All right, guys. So this is a podcast on shock. This is one of 4, maybe 5 small 15-minute podcasts. And what we're going to talk about is shock, the different forms of shock, and basic advanced life support management for shock. But before we can really break down and go into shock and the management of shock, we kind of got to understand what's taking place inside the body, more so on a compensatory level inside the body. So this first podcast is going to be pretty much how the body compensates for the early stages of shock. All right, so what is shock? We've all heard it throughout our EMS career. Shock is decreased blood pressure, which is not the term for shock. That's usually the first thing people say. Shock is, by definition, hypoperfusion, which all that means is decreased perfusion. And to make that even more interesting, so to say, speaking wise, that means the O2 delivery to the cellular site is less than the O2 demand at the cellular site, meaning the O2 demand is greater than the amount of oxygen that's being delivered to the cellular site for normal cellular functioning. Now, to better understand that, we kind of have to understand cellular respiration / cellular metabolism. We know that there's 2 forms of cellular respiration that we talk about. You have aerobic and anaerobic. Aerobic, which is known as normal cellular respiration and metabolism, means it is with oxygen. Aerobic, think doing aerobics. What happens is oxygen is introduced and it is transported via the electron transport chain, and it goes into the Krebs cycle, and that process then forms ATP. Now ATP is nothing more than energy for our cells to utilize for their normal functioning. Well, that's normal cellular respiration and metabolism. When we deal with shock, we move from a normal state to an abnormal state, which is our second form of respiration or metabolism, and that's called anaerobic. Now remember, anytime you see that letter A or an in front of a word in the medical world, all that means is without. So anaerobic, well, if aerobic was with O2, anaerobic means without O2. So without O2, you have decrease in ATP production. Now, it does not go obsolete, ATP, because some ATP is actually made without the without the presence of oxygen. However, there's not enough made for normal cellular functioning. So you have a decrease. Now, ultimately, that cell does not have enough energy to function, then it will begin to die. Secondary to that, you also have, due to decreased O2, you have a buildup of lactic acid. So now if you go step to the number 1, normal cellular respiration, once O2 is broken down and all that, you form water and CO2. That's normal byproducts of cellular respiration in the aerobic state. In the anaerobic state, the byproduct of cellular metabolism is lactic acid instead of CO2. So not only do you have cell death, but you also have an increase in lactic acid, which contributes to that cell death. Those combined together gives you metabolic acidosis. Now, there's other forms of metabolic acidosis that we talk about in the medical chapters and stuff like this, but this is metabolic acidosis secondary to shock. And now that carries us back over here to where it talks about decreased perfusion causes a decrease in pH. We know that decrease in pH means we're putting ourselves into an acidotic state. We kind of live in an acidotic state, borderline, because we know that normal pH is 7. Not acidotic, but a more alkalotic state, because a neutral pH is 7. Well, a normal human body is 7.35 to 7.45. So we actually are on the right side or the high side of normal, so that puts us in an alkalotic state. Well, during shock, due to that decreased perfusion, decreased oxygen demand, that buildup of lactic acid, cellular death, and that protein release and all that, we start dropping our pH. Now that will cause cell death, which can lead to organ failure, and then ultimately lead to death. So to better understand shock, now that we got a little better grasp of cellular respiration, we're going to talk about some core organs in the body that contribute to the compensation of early stages of shock. You've got your brain. Mainly we're going to talk about the medulla and the posterior pituitary gland. Then you got your heart, and your vessels. Now, we're really going to key in on this little podcast talking about the vessels, mainly the carotid bodies and the aortic arch. And we'll talk about those in specific due to a baroreceptor and the chemoreceptors that we learned about in first semester and their functions. And then we're going to talk about the kidneys, more so the adrenal glands that sit on top of the kidneys, but the kidneys do play an important role also. So, heart, not obsolete. It does play an important role. However, that role comes from, sorry about that, our role comes from very simple, generic, basic understandings. Increases heart rate, decrease heart rate, increase heart rate, increase contractility. So that's how it kind of compensates. It's got a very basic compensation method. Now the vessels, they trigger a lot of things to take place. So what happens in shock? So we go back up here and we know we got a decrease in perfusion. We have, which causes a decrease in MAP. MAP is what we call mean arterial pressure. Now how does our body know we have a decrease in MAP? Because of those baroreceptors. So if we go right over here and we look inside our aortic arch and our carotid bodies, we have two specific type of receptors there. We have baroreceptors and chemoreceptors. Now the chemoreceptors do play an important role because they do detect that changes in pH balance, especially the plasma secondary to CO2 and lactic acid buildup, but we're more so going to talk about the baroreceptors in this. Now, anytime you hear the word baroreceptor, I want you to think stretching. Okay, so let's talk about something away from shock. Let's talk about high blood pressure and how a baroreceptor works, because it's easier to explain that. So what happens in that aortic arch and that carotid body when our blood pressure increases? That pressure inside the lumens of our vessels causes the vessels to stretch out. Remember, stretch, baroreceptor. And once it reaches a certain point, those two spots where those baroreceptors are located, the common carotids and the aortic arch, are innervated by two specific cranial nerves. In the aortic arch, you have cranial nerve 10, which is a vagal nerve, or vagus nerve, and then in carotid bodies you have cranial nerve 9, which is your glossopharyngeal nerve. So once these baroreceptors stretch out past that certain predetermined limit that your body has, it sends a signal via those cranial nerves to the medulla. Now once the medulla processes it and says, hey, we need to do something about it, so it sends a response down the spinal cord and it exits out the thoracic, and it causes the heart rate to decrease by innervating the SA node, and it decreases the automaticity and the electronic firing or electrical firing of the heart via the AV node, and causes the heart rate to drop down, which ultimately will decrease the stroke volume. Because remember, cardiac output, not stroke volume. What is the formula for cardiac output? Stroke volume times heart rate. All right. So how does all that little part work? So inside your medulla, you have two areas. Those two areas are called your cardioregulatory center and your vasomotor center. Now your cardioregulatory center has two sections inside it. You have your cardioinhibitory system, and then you have your cardioacceleratory system. Now, how does your cardioinhibitory system work? Just like we were talking about in that previous example, those pressures increase, the baroreceptors stretch beyond that predetermined limit. It signals via the cranial nerve 10 and cranial nerve 9 to the medulla. The medulla sends that impulse down the spinal cord, causing the SA node to decrease the firing rate and AV node to decrease the conductivity of the ventricles, therefore decreasing the heart rate. Now, this is all done via the parasympathetic nervous system. Now, do you understand that? Let's take the flip side for shock. The same concept takes place, except instead of having high pressures, we have a low pressure. So now those stretch receptors have decreased down, and they're not beating that minimum resistance or minimum stretch that the body has predetermined to be normal. So what happens is those same cranial nerves stimulate the medulla to send those impulses down to say, hey, we need to increase blood pressure so that we can increase MAP. How do we do that? The cardio-excitatory system inside the medulla sends that impulse down the spinal cord, and we activate the sympathetic nervous system, which causes an increase in heart rate and causes an increase in stroke volume. What is our formula for cardiac output? Heart rate times stroke volume. So how do we increase our stroke volume? We're going to pull that in just a second when we start talking about our kidneys and our posterior pituitary gland. So going back up, remember I told you there were two sections inside the medulla. You have your cardioregulatory center, and then you have your vasomotor center. So how does the vasomotor center get stimulated? Once the cardioexcitatory system is stimulated, it causes an immediate response to the vasomotor center. Sorry about that. Vasomotor center that stimulates an impulse down the spinal cord to innervate the adrenal glands that stimulates the release of epi and norepinephrine. This then stimulates alpha-1 sympathetic receptor sites, causing vasoconstriction. So there's where your vasoexcitatory system comes into play. Vasomotor system. So let's talk about the second section. We're going to talk about our kidneys, and again, mainly our adrenal glands. So once all this takes place up here with the heart and stimulates these receptor sites, and we have an increase in heart rate, an increase in vasoconstriction and all that, it also increases our CAMP production. Now, this increase in CAMP causes our kidneys to release renin. Now, once renin is put into the blood system, it combines with a protein that is formed inside the liver called angiotensinogen. Once renin combines with angiotensinogen, you form angiotensin 1. Now, angiotensin 1 is floating through the blood, and it comes in contact in the lungs with what we call ACE. ACE is angiotensin converting enzyme, and that converts angiotensin 1 to angiotensin 2. Now, angiotensin 2 is where we start having some responses come in. It causes an increase in thirst. Now, that makes the body want to bring in fluid, so we start drinking fluids, which increases our stroke volume, or fluid for volume, which then in turn increases stroke volume. We have vasoconstriction because it comes around and taps that vasomotor response system also. And we have an increase in the production of, or the release of, aldosterone secondary to the adrenal cortex stimulation. Now, how does aldosterone work? Aldosterone works by causing the kidneys themselves to increase the absorption of sodium. So what do we remember about sodium and sugar? What follows sodium and sugar? Water, right? Think about a diabetic. When their blood sugar is high, they're urinating a lot. Why? Because the body's trying to get rid of that sugar. What comes behind that sugar? All the fluid, which makes the urine. Okay? So as this sodium starts reabsorbing, so does water. And again, that reabsorption of water increases in circulatory plasma volume, and that causes an increase in our mean arterial pressure, along with our venous return to the heart, which is our preload. So we'll go back up here to that cardioexcitatory system that I was just talking about, and that gives us that increase in stroke volume. So now, aldosterone also stimulates our posterior pituitary gland. It's located here up there with our brain, and that actually, the aldosterone itself doesn't stimulate that posterior pituitary gland to work. Actually, what it does is aldosterone causes us to increase our sodium absorption and changes our osmolarity of our blood. So that increase in the osmolarity of our blood due to that sodium absorption from the kidneys then stimulates the release of the antidiuretic hormone. The antidiuretic hormone causes a further increase in sodium and water, which again causes an increase in stroke volume. So that is kind of how the three main components of the body, the brain, the heart / vasoresponse system, and our kidneys and adrenal glands function in producing compensatory measures for the body. Now, they're not saying that that's the only 3 special organs of the body that work. The lungs work too, because they increase respiratory rate to increase the amount of oxygen. They increase their volume to increase the amount of oxygen. All the organs are playing an important role, but these are the 3 main ones that are doing something on both sides of the table to try to compensate for that decreased amount of oxygen supply. So that is basic shock patho in a nutshell. Now it can get way deeper, especially when you start talking about this renin-angiotensinogen. That's your RAS system. I'll have a whole nother podcast on it. I really think the RAS system is actually pretty unique and pretty interesting. There's one on cellular respiration where we talk about the Krebs cycle and all that, but that's your basic hemodynamic response or compensatory measure for shock.